on to section 5.5, which is our last section in chapter 5 on our first little chapter on integration with the substitution rule is how we're going to end. It is much easier to take a derivative of many types of functions than it is to integrate some functions. So taking antiderivatives can be more tedious in some cases. Now this section will kind of expand our knowledge on how to take an antiderivative. For a family of functions that you will see are ones that incorporate the chain rule in their derivatives. So basically we're looking at composition functions here and knowing how to integrate those composition functions. And we're going to do it by a little substitution, because in math sometimes we can kind of change things up a little bit to make life so much more easier. So here we go for the substitution rule for indefinite integrals. So we are going to start by saying u is equal to g of x, where g is differentiable on an interval, and we're going to let f be continuous on the corresponding range of g, so the corresponding y values of that g function. On that interval, the integral of f of g of x, g prime of x dx. So hopefully you recognize this as the chain rule in here. I've taken the derivative of the inside kind of function there is going to equal f of u du. Now I know that's just kind of some terminology. Things can be proved in here, so how are we really going to use that? Well, here are some of the procedures that we're going to use. All right, so for the substitution rule, number one, we are going to be given an indefinite integral involving a composition function f of g of x. We need to identify the inner function g of x, and when we do that, we're going to call that u, such that a constant multiple of g prime of x appears in the integrand. So what that means is you're kind of looking to foresee what you have in the problem to be able to kind of change out into terms of u. And in order for that to happen, a constant multiple of the derivative has to be in the integrand. Remember what the integrand is? It's this function here that we're integrating. And so then number two, we want to substitute u equaling g of x and du. So if I take the derivative of this du, then I take the derivative of that in terms of x. So with our differentials, we can say that du is equal to g prime of x dx. And we're going to substitute that into the original integrand. Number three, we're then going to evaluate the new indefinite integral with respect to our new variable, which is u. And then we're going to go backwards in terms of x. So we can't leave our answer in terms of u, because that's what we did not start with that. So we have to go back in terms of x by using u equaling to g of x. Now I know sometimes that might, again, look foreign to you as well, but that's kind of the procedures that we're going to take. Hopefully by example, you'll kind of get the hang of how that we do this substitution. All right, so let's look at these first two integrals, and these are going to be our most basic because everything's going to be there for us, but not all the time is that the case. So we're going to use the substitution rule to find the following indefinite integrals. Now, the first part is probably one of the key parts because you got to find and locate that inner function. The inner function of that composition function. So I want you to focus on if there is a power or if there is an angle of a trig function, what is within each one of those. So for example, this one, I have a power. I have something to a power. I want you to recognize that something as your u. Okay? So you'll see why that's the case here in just a second. So anytime you have a power, then try to let what's inside of that power equal your u. So in this case, I'm going to let u equal the function 2x plus 1. Now, I need to check out what g prime is, okay, or what du is, so that I can kind of plug some stuff in. So first thing is identify u. Now take the derivative of this. So du, the derivative of that, what's the derivative of this function? This is where the differentials, I believe it was in section 4.9 or 4.6, maybe 4.6, is going to be important because you take the derivative of this, take the derivative of this function, but then you have to do the differential of dx at the end. So the derivative of 2x is 2. The derivative of 1 is 0. But then I have to put my differential here, dx, so that I know I took the derivative of this with respect to x. I took the derivative of this with respect to u. So that's where I get my du. Now, let's figure out what we have here. I'm going to now substitute in terms of u now. Okay, so here, this I let u, but it's to the third power, so I'm going to write that as u cubed. But look at what du is, because in order to integrate this in terms of u, I need a du back here. Well, a du is 2 dx. What do we see in the integral that's left? 2 and dx. So all of this I can exchange as du. And that's what I want to do. So you have to be very careful here to make sure you have all pieces accounted for when you're changing your integral in terms of u. So here I have my u cubed, and everything else is my du, so therefore I now in terms of u can integrate this very nice power function in terms of u. So what is that? Well, that means I have to add 1 and divide by that new power. And then don't forget this is indefinite, so now we're back to our arbitrary constant that we must have within our function. Now, this I did the integral. That's what we needed to find. But now I'm in terms of u and not in terms of what I started with. So I've got to go back. What was u equal to? Now I have to take 2x plus 1 and put it back into my function. Now, in this case, there's lots of ways you could write it. You could go 2x plus 1 to the 4th power all over 4 plus c. That is one way to write it, but I'll tell you, I most of the time will bring out the fraction and say, okay, that's 1/4 times 2x plus 1 to the 4th power plus c. So either way will work. Again, if it's a multiple choice in my lab math, you're going to have to make the right choice as to what's equivalent to what you have. Okay? All right, very good. Next one, have a trig function. And when you have trig functions, most of the time with these types of problems, either the trig function is going to yield another trig function for its derivative, and that's what's going to be kind of our u, or you're either going to have the angle being equal to u. So notice here I have an angle that has an inside function of x squared. So remember, trying to find that inner function, and you may take a couple to kind of see what the actual inner function is. But I'm going to take that inner function, which is this angle this time, and let u equal x squared. Because if I let u equal x squared, if I take the derivative of this, it's technically 1. With respect to u is du with that differential. Then I take the derivative of x squared to get 2x, and in terms of x, that is dx. So we need to line things up here. So what is u? U is x squared. So I'm going to change x squared into a u. But what do I know about du? I have everything else in that integrand that matches up with my du. So therefore, all of these pieces are du. And that I want to exchange, again, substituting to a function that it's manageable in order to integrate. So here, I need to integrate cosine of u. Well, that's one of our basic ones. What do we take the derivative of to get cosine as a derivative? It is the function sine. So I get the sine of u. Don't forget about your plus c with an indefinite integral. So once I've integrated, all I'm one step away is to plugging in the u and saying that this is sine of x squared plus c. And that right there is your answer. Now, the next statement is really important because you can always check your work with these. If you take the derivative of your answer, you should get back what the integrand is of your original problem. And so remember, you can always derive your resulting function to check your work. Now, these are what we call perfect substitutions, I guess you could say. But not all of the time does your du kind of line up with what's left over, or your du line up with what's left over. Sometimes you got to modify things just slightly, okay? And that's what we have here with these next two problems. So I'm going to look for that innermost function. Notice here I have an x to the 4th, and then I have an x to the 5th plus 6, but I have that to a power. So notice, if I let this be my u, what's the derivative of an x to the 5th? The derivative of an x to the 5th is an x to the 4th. And so that might be helpful in my du case. So let's let u equal the expression that is raised to a power. So I get x to the 5th plus 6. du, take the derivative of u, that's 1. With respect to u is du. Take the derivative here, I get 5x to the 4th. This gives me a 0, but I have to tag on my dx because that is the derivative that I'm taking the variable I'm taking the derivative with respect to. So, what do we have now? Well, if I go and try to do my substitution, this is my u, so I would get the integral of u to the 9th. But when I try to go and do my du here and match up the things that I have left over, notice that I have a dx. That's good. Maybe I should color code this. I have a du, or a dx, which is right there. I have an x to the 4th, which is right there, but notice I don't have a 5. But the beauty of math is that I can account for that 5. So that means that if I need a 5 here in order to have my du, that means it's basically I'm going to be changing the way my function looks by trying to do products of 1, which doesn't really change the function, it just changes the way it looks, if you're multiplying by things other than 1. So if I need a 5 here, what do I multiply 5 by to get 1? Well, it would have to be its reciprocal, which is 1/5. So 1/5 of 5, if I were to simplify those are going to cancel themselves out, but we don't want them to cancel out because I need this extra 5 for my du. So now I can exchange all 3 of those for a du in my problem. But the thing about it is I still need that 1/5 out front. Okay? So that's the trick, and these are the things you want to practice in this section to master this concept of substitution with integrals. So let's go ahead and integrate our u to the 9th. I'm going to add 1 and divide by that new power. Do not forget about your plus c that we have at the end. Now you can do your plus c in here, but if I do a constant of a constant, it's still a constant. So just worry about putting it outside. Now, final step is to take u out and plug in what u is equal to. So this now has to go right in there. So I'm going to go ahead and multiply these, which would end up with a 1/50th. And then I have that x to the 5th plus 6. Raise that to the 10th power plus c. And that will be our answer. So there's a family of functions because of that arbitrary constant that's going to work for this answer. But you also, remember, can do the chain rule on this to see if you get back what you started with. When you bring the 10 out, you get 10/5, which is 1/5. Then you multiply by this with a decreased power, which would be to the 9th. But then you have to take the derivative of the inside, which would be a 5x to the 4th. So the 5 on your chain part is going to cancel the 1/5 that you had there, leaving us with what we started with. Okay? All right. What do we let u equal in this problem? In this problem, I have 2 trig functions. It's not like this last one where I only have 1 trig function with a changed angle. Okay, so anytime the angle is changed, hone in on that. This time the angle is not changed, but I do have a trig function that is to a power. So remember, I could write this like this if I wanted to. Okay, those are the exact same things. So you want to make sure that you take note of that, okay? What is the inner function? And that sometimes is the hardest of what you may have to try a couple things. All right, so remember, if I have an outside power, focus on what's inside of that power. So I'm going to choose for now to let cosine equal the inner function. The derivative with respect to u is equal to, what's the derivative of cosine? It is, starts with a c, so it's negative, sine of x dx. And that's what I want to be able to plug in. All right, so let's change in terms of x in terms of u. So I'm going to plug cosine of x. I'm going to put a u where cosine is. And that function tells me I have to cube that. But notice what happens here. I have the dx and the sine, but I'm missing the negative. So that means that I need to throw a negative here. Well, it's like a -1. What would kind of cancel that out in a way? It's if I throw a negative out front as well. Okay, so now I get negative out front, and all of this now is my du. So it's almost like you have a puzzle that you have to fix. And you have to make sure that you have all the missing pieces in there before you can integrate. So we are now going to, once I've changed it in terms of u, this should be the easy part, to integrate u to the 3rd. So I add 1 and divide by the new power. Don't forget your plus c. And then I'm going to take it back in terms of x. So I'm going to extract out the 4 in the bottom and make that a negative 1/4 out front. Then what was u? U is cosine. So you can write it as cosine of x to the 4th power plus c. Or you could bring that power on the inside. So negative 1/4 cosine to the 4th of x plus c would also be an acceptable answer for this problem. Again, if you're looking for multiple choice answers on my lab math, then you have to decide which one works with which one. Okay? All right, very good. Now, here's one with a twist. We just don't like those same types of problems. We want to do a little twist here. So, here we have the integral of x all over the square root of x plus 1 dx. Now, as a reminder, this in the denominator is actually a power. With a square root, it's a fractional power of 1/2. So you want to make sure you realize that. So anytime before I said focus on that expression that has a power, that might be your inner function. So let's go with that. If I let u equal x plus 1, we always take the derivative of that, so we can kind of exchange things out. Well, the derivative of u is du with respect to u. Derivative of x is 1. Dx, the derivative of that is 0, so we have 1 dx. Okay, we normally don't write the ones. So when I try to go and substitute in terms of u, what I get here is this. This, I can do u to the 1/2, no problem. Here, dx is the same as du, so I could take this dx out and plug in du, and here lies the problem. The problem is, I have this extra x up here that wasn't needed in my derivative, so what am I going to do with it? Well, if I got to get it in terms of u, and I need to replace x, I should know how those things are related. Well, we've decided how they are related right here. So if you take the equation that you designated for u equal and solve it for x, then we can make that final substitution to make our problem work. And it's going to be very nice. So if I want to solve for x, I'm going to bring this 1 over. X is equal to u minus 1, and that's what we have to put right in the top to get everything in terms of u. So now, the integral is just a little bit more difficult than what a straight little power substitution is like our last two examples, but it's very, very much doable. We did these types of problems where I can split this fraction up, and that's the way that you want to do that, so you can get a power. Now, when I split that fraction up, remember that's a u to the first divided by u to the 1/2. Subtract those exponents, I get u to the 1/2. Minus, do not forget to give u to the 1/2 in the bottom to both terms in the top. So I get 1 over u to the 1/2, which I can write that as a negative exponent so that I can then integrate both of those separately. Okay? Now, granted, these aren't the prettiest because they are fractional exponents. So when you add 1, you're going to get a fraction. When you divide by the fraction, it's the same as multiplying by that reciprocal. So if I add 1 to 1/2, I get u to the 3/2. Don't divide by 3/2. Multiply by the reciprocal, which is 2/3. Then I'm going to subtract from that. When I add 2/2 to negative 1/2, then I get u to the 1/2, u to the positive 1/2. Again, don't divide by 1/2. Multiply by the reciprocal, which is 2 over 1. And then don't forget your plus c. After you've integrated every single term, make sure you do your plus c. Now our final process is to take the u out and put in what u is equal to. And in this case, u is equal to x plus 1. So final answer is going to be 2/3 times an x plus 1 to the 3/2 minus 2 times an x plus 1 to the 1/2 plus c. Obviously, if you were to check your work and take the derivative of this, you would then have to kind of combine a lot of stuff in order to get back to what you started with here. But that's okay. Those things should be equivalent. All right, very good. The last big section here of chapter 5 is doing substitutions with definite integrals. So now, instead of having no limits of integration, now we have limits of integration. And how do we account for that? When you don't have any, we have the plus c. when we do have limits of integration, we're going to be able to get our final answer down to one number. So remember, an application of this is that we're finding the net area of this function from, say, -1 to 2 of this function. So we've just expanded the family, or the amount of functions that we can take an integral of. All right, so the substitution rule is also used for definite integrals. In fact, there are two ways to proceed. Now, you may use the substitution rule to find an antiderivative, just like what we did up here, and then change back to the original variable, just like we did up here in terms of x, to use the fundamental theorem of calculus to evaluate f of b minus f of a. So keeping the same integrams that you originally are with, so in this case 0 and 2, you can go back in terms of x and plug it in. Alternatively though, this is the way that we normally do things, not that you have to do them. Once you have changed your variables from x to u, you also may change the limits of integration and then complete the integration just in terms of u, okay? So this tends to be the most efficient way, but not to say that's the only way that you have to do it. So by definition here, let's let u of x equal g of x, which is that innermost function of your composition function, where g prime is continuous on AB, and let f be a continuous function on the range of g, then the integral from a to b of f of g of x, times g prime of x dx, so this is incorporating that chain rule type thing, is equal to the integral from g of a to g of b of f of u du. Okay, so basically I have to plug in that a into my g function and figure out what the new u is. Plug the b into the g function and figure out what the upper limit in terms of u is. And then I can integrate that and evaluate at those two values. So let's look at what that means and what it looks like. All right, so we have we have a definite integral now that we want to integrate. So just like before, the process we were taking is exactly the same with definite and indefinite. We're going to choose a u. And in this case, I need to choose the u that is actually of a power. So I'm going to let u equal x plus 3. Then I'm going to take the derivative of u, which is 1, times du, which is the differential. Derivative of this is 1, derivative of this is 0, so the derivative is 1 in terms of x, which would be dx. And I'm going to sub things in now, okay? So we want to integrate. Now notice here, this is my u to the third power, but I don't want it in the denominator. So I'm going to go ahead and one step bring that power up and make it negative. And notice that this matches with that, so therefore I can substitute. It was a straight substitution in this problem. Now, we don't want to use 0 and 2 because this is x equals 0 and x equals 2. So if x equals 0 and x equals 2, then I need to know what u is in order to evaluate in terms of u. Okay, so what do we do? Well, I'm going to take 0. How are x and u related? It's this equation right here that we've created. If I plug 0 in for x and add 3, then my lower limit is now 3. If I plug 2 in here and I add 3, my upper limit now is 5. So now I'm going to change my limits of integration from 3 to 5, and now I don't have to go back to x at all. Okay, now you can go back in terms of x like what we did before, but then you have to use 0 and 2, which might be okay because you have a 0, but a lot of times it's a lot more work, okay? All right, so let's integrate. I'm going to integrate u to the minus 3. Well, I'm going to add 1. So remember, when you're in negative, make sure you add 1 to get a minus 2 and divide by that new power. And here, I want to evaluate at 3 and 5. Now, I'm going to go ahead and bring out that negative 1/2 so I don't have to worry about working with a fraction on the inside, but actually I do. I should have thought before I spoke. U to the minus 2 is 1 over u squared that I would have to evaluate at 3 and 5, but then I don't have this extra 2 hanging out there, okay? So you do it however you see fit. I want to throw in 5 and square it, so I get 1 over 25 minus, throw in 3, I get 1/9, and now it's just some calculations that we have to do. Okay, if you were to get a common denominator with 25 and 9, it is 225. So it would be 9 over 225 minus 16 over 225, which gives us negative 1/2 up front, negative 16 over 225. And I can multiply these fractions together, cancel my 2's, change my negatives to a positive to get a final answer of 8 over 225. Okay. All right. So again, we could have integrated here. Let me kind of change color and show you what I mean by keeping it in terms of x. If you were to go like right here and in terms of x, I would have negative 1/2 times a 1 over x plus 3 squared. Now you could go ahead and choose the lower and upper limits of integration as you had before and plug it in, but you're still going to get the same thing here. So instead of going back and forth of variables, a lot of times doing this change of variables and changing of your limits of integration is very, very handy. Okay? All right, let's try this one. What are we going to let u equal? I see a power, and with that power, I get x cubed plus 2. That is the u that I want to designate. And so here, actually, I'm going to change this to a 2. If it's not on your paper to a second power, make sure you change that to a 2. So here, I'm going to take the derivative of u, which is du, with my differential. I'm going to take the derivative of x cubed plus 2 to get a 3x squared times the dx, the differential with respect to x. And now I need to make sure I have all my pieces. So I'm going to integrate, remember this was my u, to a minus 2 this time. But do I have all of my du? I have dx and I have x squared. I do not have that 3, so I need a 3 inside here, which I compensate for that on the outside by the reciprocal. So I need a third of 3. Remember, these are going to be 1. It doesn't change the values that we're working with. It just changes the way things look. So now what I have right here is all of my du. So I finally end up having my u to the minus 2 du. Now let's go ahead and change our limits of integration. I have x equaling negative 1 and x equaling 2. So what does u equal and what does u equal here? Well, throw negative 1 in. Cubed is negative 1 plus 2 is 1. Throw in 2. 2 cubed is 8 plus 2 is 10. Excuse me, not 11, 10. Okay, and so those are our new limits of integration. From 1 to 10 is what I want to integrate in terms of u. So let's do that. I have my 1/3 that I need to keep. And I'm going to add 1 to my power to get a minus 1, but I have to divide by the new power, which is negative 1, evaluate at 1 and 10, and now we do our calculations for our fundamental theorem of calculus. So I'm going to go ahead and bring the negative out front as a negative 1/3. And I'm going to write this as 1 over u for the fraction that I'm evaluating at 1 and 10. So I'm going to plug 10 in, I'm going to plug 1 in, so I get negative 1/3 times 1/10 minus 1. And so, negative 1/3 times 1/10 minus 1, so 1/10 minus 10/10 is negative 9/10. And I can cancel the negatives. I can do 3 into there to get a final answer of 3/10. That would be my final answer there. Okay? All right, very good. Last two, trig ones. Last one's going to be just slightly tricky. It's not as straightforward as this first one. This first one is similar to one we had on the reverse side, on the indefinite. Notice the angle is not changed whatsoever, so I'm probably going to focus on that power. What function is to that power? It is sine of x, so I'm going to let u equal that. I'm going to take the derivative of u, which is 1, with respect to u is du. Derivative of sine is cosine of x dx. And so now I'm going to sub in what I have. So I want to integrate. Notice here, this is my u to the 4th power. And all of this is all here. So there's no modifications that I have to do on my function whatsoever. So here, I need to now change my x equaling 0 and x equaling pi over 2 to what they are equal to in terms of u. Okay, so if x equals 0 and I take the sign of 0, then I get 0 again. If I do pi over 2 in for sign, the sign of pi over 2 is a 1. So I would much rather do things with 0 and 1 than with 0 and pi over 2. So let's make those our new limits of integration. And now we get to integrate using fundamental theorem of calculus to evaluate. So I get u to the 5th, divide by that new power, evaluate at 0 and 1. So I'm just going to extract out the 1/5. So basically, I have to evaluate u to the 5th at 0 and 1. You could skip this step if you're okay with writing it out to where you can see plugging in 1 to the 5th is 1, plugging in 0 to the 5th is 0. Therefore, my final answer is 1/5. So again, integrating in terms of u is not bad, and evaluating in terms of u is even more efficient sometimes than what we would have before. Okay, last problem in chapter 5. Here we go. Now, this one is a little bit tricky because I'm going to first let u equal the trig function that is to a power. So again, there's no angle change here. It's just x. So that can't be what u is equal to. I need to look at the power. What's the trig function to the power? And that function is cosecant of x. Again, get rid of the powers when you designate what u is. So I'm going to take the derivative of this with this du. Now, you might have forgotten the derivative of cosecant. Not one that we use quite often, but it is something that you definitely need to know. So the derivative of cosecant is actually negative cosecant of x, cotangent of x, dx. I have to squeeze it in there. Negative cosecant cotangent of dx. Now, if you go and say, okay, I'm going to integrate here, and I'm going to exchange that for u and take it to the 4th power, the problem is here is that I don't have everything I need for du. I have a dx, I have a cotangent, but if I let u to the 4th be my power that I'm working with, I need an extra cosecant. So what happens is that I need to think of this as cosecant cubed of x. I'm stealing one basically from here. And I'm going to redistribute that in a sense over here with the cotangent so that I have enough for my du. And that's the tricky part there, okay? You got to kind of assess what you have and what you need and what's going to be left over, okay? So here's my dx, there's my cotangent, there's my cosecant, but we have to adjust for our negative. So I do need a negative here, which means I need a negative on the outside. So I need an eraser here because I need to get rid of that power. That power is no longer going to be a 4. What is that power going to be? That power is going to be this cosecant to the 3rd power, and all of this with my negative is my du, and that's what I'm going to integrate. So that's why this one's just ever so slightly trickier than the other. Now, problem is I don't have my limits of integration here. I need what u equals when x equals pi over 4. So you probably might need to do a little reminder of some of those values for trig. If I have x equaling pi over 4 and I plug it in, I need to know what the cosecant of pi over 4 is. Well, I'm going to think about a 30-69, or excuse me, a 45-45-90 right triangle, which is something like this. And so however that you remember how your trig functions are, I like to use my triangles. Cosecant is the reciprocal of sine. So if I know the sine of pi over 4, which this is a pi over 4 angle in my 45-45-90, then the sine is going to be 1 over root 2, but the reciprocal of that will be root 2 over 1. So if x equals pi over 4, then u equals root 2. Now if I plug in x equaling pi over 2, I need to know what the cosecant of pi over 2 is. Well, that is thinking of it as the reciprocal, and I changed that. Now what is the reciprocal of 1 over sine of pi over 2? Sine of pi over 2 is going to be 1. 1 over 1 is 1. So that might be a little bit of tricky for you to evaluate what those are on those special angles. But once you have it, it's pretty nice. We get root 2 to 1 as my new upper and lower bounds. Okay? So if you want to integrate and go back in terms of x, you can. But again, this one's pretty nasty with the cosecants and cotangents and stuff. I'd much rather just stay in terms of u. So we are going to integrate u cubed. Means I add 1 and I divide by that new power. And I'm going to evaluate at root 2 and 1. But don't forget you have that negative out front as well. So when I plug 1 in, 1 to the 4th is 1. So I get a 1/4 minus root 2 to the 4th power. Well, that's 2 to the 1/2 to the 4th power. So a base to 2 powers, I can multiply those powers and I get 1/2. So 2 to the 1/2, which is the same as, excuse me. That's not 1/2. Hello. 2 to the 1/2 to the 4th. Multiply those, I get a power of 2. Excuse me. So I end up with a 4 when I take root 2 to the 4th power. But when I divide it by this 4, I get a value of 1. So be very careful. If you need help with that with your scientific calculator or graphing calculator, please use that as an advantage. 1/4 minus 1 is a negative 3/4, and therefore the opposite of that is going to be positive 3/4 as a final answer. So there you have it. The end of chapter 5, which gives us a lot more techniques in order to integrate some of those more difficult functions in a different way to where you can substitute very nicely and very slickly into a different variable in order to integrate that function. So try to master these, try to work with that, make sure you look for what the inner function is and then go from there to figure that you have all pieces. So until next time.